Please take a moment to settle in, expand your screen if you can, and consider subscribing if this resonates with you. Now, let us begin. We exist within a region of space that may not behave the way we assume it should. This is not a statement of science fiction or speculative cosmology divorced from measurement. It is a recognition that emerges from the accumulation of precise observations, from the behavior of light across billions of years of travel, from the motion of galaxies, from the distribution of matter, and from the stubborn refusal of certain numbers to align with the predictions that our most successful theories generate. To understand what it means to say that physics does not add up here, we must first understand what it would mean for physics to add up at all, and then we must confront the evidence that suggests our local cosmic neighborhood, vast as it is, may occupy a region where the rules we have written down do not fully describe what we see. Physics, at its foundation, is not a collection of facts, but a framework of expectations. It is built on the assumption that certain principles hold everywhere and at all times. Conservation laws, symmetries, invariances under transformation, these are the pillars. Energy is conserved. Momentum is conserved. The speed of light in a vacuum is constant for all observers, regardless of their motion. The laws of physics are the same in every inertial reference frame. Space is, on the largest scales, isotropic and homogeneous, meaning it looks the same in all directions and at all locations, at least when averaged over sufficiently large volumes. These are not merely observations, but axioms, the starting points from which the entire structure of modern cosmology and particle physics is constructed. When we say physics adds up, we mean that observations conform to predictions derived from these principles. We mean that the equations we write down, when solved, yield numbers that match the numbers we measure. We mean that the universe behaves as though it follows the same script everywhere. But what if it does not? What if the region of space we inhabit, extending perhaps hundreds of millions of light years in every direction, is not a fair sample of the universe as a whole? What if the local properties of space-time, the local density of matter and energy, the local expansion rate, the local values of what we call constants, differ enough from the cosmic average that our measurements, no matter how precise, lead us to conclusions that do not generalize? This is not idle speculation. It is a possibility that has been explored, debated, and in some cases quantitatively modeled in response to a series of observational tensions that have grown sharper over the past 2 decades. Let us begin with the expansion of the universe itself. In the early 20th century, Edwin Hubble observed that galaxies are receding from us, and that their velocity of recession is proportional to their distance. This relationship, now called Hubble's law, is expressed through a single number, the Hubble constant, which quantifies the rate at which space itself is expanding. If the universe is homogeneous and isotropic, then this constant should be the same everywhere, and its value should be derivable from measurements of the early universe or from measurements of the late universe. And these two methods should agree. They do not. Measurements of the cosmic microwave background, the faint glow of radiation left over from the early universe roughly 380,000 years after the Big Bang, yield a value for the Hubble constant of approximately 67 kilometers per second per megaparsec. This value is derived by fitting the observed pattern of temperature fluctuations in the microwave background to a model that includes the density of matter, the density of dark energy, the density of radiation, and the curvature of space. The fit is extraordinarily good. The model, called lambda cold dark matter, or LCDM, describes the early universe with remarkable precision. But when astronomers measure the Hubble constant using observations of the late universe, using supernovae as distance markers and the redshifts of their host galaxies as velocity indicators, they obtain a value of approximately 73 kilometers per second per megaparsec. The difference is small in absolute terms, but it is large compared to the uncertainties in the measurements. The two values disagree by about 9%, and the disagreement persists across multiple independent teams, multiple methods, and multiple refinements of systematic error. This discrepancy is known as the Hubble tension, and it is not easily dismissed. If the universe were truly homogeneous and isotropic, If the laws of physics were the same everywhere and at all times, if the expansion rate were governed by a simple, smooth evolution from the early universe to the present, then these two measurements should converge. The fact that they do not suggests one of several possibilities. The first is that one or both measurements contain unrecognized systematic errors, subtle biases in the data, or the analysis that have eluded correction. The second is that the standard cosmological model is incomplete, that there is new physics, a new field or particle or interaction that affects the expansion history in a way not accounted for by lambda-cold dark matter. The third possibility, quieter and more unsettling, is that we are not in a typical region of the universe. We may be inside a region where the local expansion rate differs from the cosmic average, a region where the density of matter or dark energy is slightly higher or lower than the mean, enough to bias our measurements in a way that makes the universe appear to expand faster than it does on average. To explore this third possibility, we must understand what it means to be in a special region and how large that region would need to be to produce the observed effect. The universe is not perfectly smooth. On small scales, matter clumps into galaxies, clusters, and superclusters, separated by vast voids where the density of matter is much lower than average. But on scales larger than a few 100 million light years, the distribution of matter is expected to become uniform, a consequence of the cosmological principle, the assumption that the universe has no preferred location. If we live in a region that is slightly underdense, where the local gravitational pull is weaker than average, then the expansion rate in our neighborhood would be slightly faster than the cosmic mean. Light traveling through this region from distant supernovae would arrive with redshifts that suggest a higher expansion rate, and we would infer a higher value of the Hubble constant. Not because the universe as a whole is expanding faster, but because our local patch is. This idea is not new. It has been studied under the name of the local void hypothesis, the proposal that the Milky Way resides within or near the edge of a large underdense region, a void several 100 million light-years across. If such a void exists, and if its density contrast is large enough, then the outflow of matter from the void, the local expansion driven by the deficit of gravitational attraction, could increase the apparent expansion rate measured by local supernovae. The question is whether such a void is consistent with observations of the large-scale structure of the universe, and whether it could produce a discrepancy as large as the one observed. Surveys of galaxy positions and redshifts have mapped the large-scale structure of the universe in increasing detail over the past 3 decades. These maps reveal a cosmic web of filaments and voids, with galaxies tracing the densest regions and vast empty spaces in between. Some studies have suggested that the local universe, within a few 100 million light-years, is slightly underdense compared to the cosmic average. Others have found no significant evidence for such a void, or have concluded that any underdensity is too small and too irregular to explain the Hubble tension. The debate is not settled. The measurements are difficult. Redshift surveys are incomplete, biased by selection effects, and limited by the finite speed of light, which means that maps of the local universe are necessarily maps of the past, with galaxies seen at different times depending on their distance. Reconstructing the three-dimensional density field from these observations requires assumptions about how galaxies trace the underlying matter distribution, and these assumptions introduce uncertainties. Even if a local void exists, there's a constraint from the cosmic microwave background. The temperature of the microwave background is not perfectly uniform. It exhibits small fluctuations, about 1 part in 100,000, that reflect the density fluctuations in the early universe. It also exhibits a large-scale pattern called the dipole, a difference in temperature between opposite directions in the sky, which is interpreted as the motion of our galaxy through the rest frame of the microwave background. If we were inside a large void, the void itself would gravitationally affect photons from the microwave background as they pass through it, leaving a characteristic imprint called the integrated Sachs-Wolf effect. This effect has been detected for individual supervoids and superclusters, but the amplitude of the signal is small and the noise is large. If the local void were large and deep enough to explain the Hubble tension, It should produce a detectable signature in the microwave background, and so far, no such signature has been unambiguously identified. This does not rule out the local void hypothesis, but constrains the properties that such a void could have. There is another way to test whether we are in a special region. If the local expansion rate is higher than the cosmic average, then measurements of the expansion rate at different distances should show a trend. Nearby supernovae, within the local region, should yield a higher Hubble constant, while more distant supernovae, beyond the local region, should yield a value closer to the cosmic mean. Some analyses have claimed to detect such a trend, finding that the Hubble constant measured from nearby supernovae is systematically higher than the value measured from more distant ones. Other analyses have found no significant trend, or have attributed apparent trends to selection effects or peculiar velocities, the random motions of galaxies that are not due to the expansion of space, but to local gravitational interactions. The evidence is mixed, and the interpretation is contentious. Let us step back and consider what it would mean, in a deeper sense, for physics to fail to add up in our region. The laws of physics, as we understand them, are local laws. They describe how fields and particles behave at each point in space-time, given the conditions at that point and its immediate neighborhood. General relativity, the theory of gravity, relates the curvature of space-time at each point to the energy and momentum at that point. Quantum field theory describes the interactions of particles in terms of fields that permeate space, with the properties of those fields depending on the local values of coupling constants, masses, and vacuum energy. If these local laws are the same everywhere, then the global behavior of the universe should be predictable from initial conditions and boundary conditions. But if the local properties of space vary from place to place, if the effective strength of gravity or the density of vacuum energy or the rate of expansion is not constant across the cosmos, then the global behavior becomes a patchwork, and our local measurements may not reflect the universe at large. This brings us to the concept of cosmic variance, the idea that measurements made within a finite volume are subject to statistical fluctuations simply because that volume is not the entire universe. If the universe is infinite, or even if it is finite but much larger than the observable universe, then the properties of our observable patch are drawn from a probability distribution, and there is no guarantee that our patch is typical. The expansion rate, the density of matter, the amplitude of density fluctuations, all of these quantities are subject to cosmic variance. The question is whether the magnitude of cosmic variance is large enough to explain the observed discrepancies, and whether such variance is consistent with the assumption of homogeneity on large scales. Calculations of cosmic variance depend on the size of the region considered and the amplitude of fluctuations on that scale. The cosmic microwave background tells us that fluctuations in the early universe were small, about 1 part in 100,000 in amplitude, but these fluctuations grow over time through gravitational instability. By the present day, density fluctuations on scales of a few tens of millions of light years are of order unity, meaning that the density can vary by factors of a few from place to place. On larger scales, fluctuations are smaller, but they are not zero. A region the size of the observable universe, roughly 90 billion light-years across, is subject to fluctuations of roughly 1% in quantities like the average density or the expansion rate. This is a rough estimate, and it depends on assumptions about the power spectrum of fluctuations and the geometry of space, but it gives a sense of scale. The Hubble tension, a 9% discrepancy, is larger than what simple cosmic variance would predict, unless the fluctuations in our region are unusually large, or unless we are near the edge of a large structure where gradients are steep. Another way to think about this is through the lens of the Copernican principle, the assumption that we do not occupy a special place in the universe. This principle has been remarkably successful. It led to the rejection of the geocentric model, to the understanding that the Earth orbits the Sun rather than the reverse, to the realization that the Sun is one star among hundreds of billions in the Milky Way, and that the Milky Way is one galaxy among hundreds of billions in the observable universe. The Copernican principle, when applied to cosmology, becomes the cosmological principle the assertion that the universe is homogeneous and isotropic on large scales. But the Copernican principle is not a law of nature. It is a methodological assumption, a guide to model building. If observations consistently require that we are in a special place, then the assumption must be revised. How special would our region need to be to resolve the Hubble tension? If we are in a void, the void would need to be several 100 million light-years across, with a density contrast of roughly 20 to 30% below the cosmic mean. Such a void would not be unprecedented. The largest known voids in the universe are comparable in size, though the precise density contrast is difficult to measure. But the void would need to be centered or nearly centered on our location, and this would represent a return to a kind of centrality that the Copernican principle was meant to eliminate. It would not mean that we are at the center of the universe, but it would mean that we are near the center of a large-scale structure, and that our measurements are biased by this location. This is not impossible, but it is uncomfortable, and it raises the question of whether the discomfort is justified by the data or whether it reflects a failure to find a better explanation. Let us turn now to another observable that does not add up: the rate at which structure grows in the universe. The cosmic microwave background provides a snapshot of the universe at a single early time, when the density fluctuations were still small and linear. General relativity and the standard model of particle physics predict how these fluctuations should grow over time, eventually forming galaxies, clusters, and the large-scale structure we see today. The growth rate depends on the density of matter, the density of dark energy, and the nature of gravity itself. If we measure the amplitude of density fluctuations today by counting galaxies or by observing the gravitational lensing of light by large-scale structure, and compare this to the amplitude predicted from the early universe, we can test whether the growth rate matches expectations. It does not, at least not in all measurements. Several independent observations suggest that the amplitude of fluctuations today is lower than predicted. These include measurements of weak gravitational lensing, where the shapes of distant galaxies are slightly distorted by the gravitational pull of intervening matter, and measurements of galaxy clustering, where the statistical distribution of galaxies in space is used to infer the underlying matter distribution. The discrepancy is quantified by a parameter called S8, which combines the amplitude of fluctuations with the density of matter. Measurements of S8 from the late universe tend to be lower than the value inferred from the cosmic microwave background by about 2 to 3 standard deviations, a tension that is less severe than the Hubble tension, but still persistent and puzzling. If structure is growing more slowly than expected, it could mean that dark energy is not a simple cosmological constant, but a dynamical field that affects the growth of structure in ways not captured by the standard model. It could mean that gravity behaves differently on large scales than general relativity predicts, becoming weaker or stronger in a scale-dependent way. Or it could mean that our local region has a lower amplitude of fluctuations than the cosmic average, another manifestation of cosmic variance or of a special location. If we are in a region where the initial fluctuations were slightly smaller, or where the density of matter is slightly lower, then the growth of structure would proceed more slowly, and we would measure a lower value of S8. This is another way in which physics might not add up here, not because the laws are different, but because the initial conditions or the local environment are not representative. There is also the question of what we mean by here. The observable universe extends roughly 46 billion light-years in every direction, a volume determined by the age of the universe and the speed of light. But the region that could meaningfully be called local, the region within which we can make direct measurements without relying on model-dependent extrapolations, is much smaller. Supernovae used for measuring the Hubble constant are typically within a few 100 million light-years. Gravitational lensing surveys probe scales up to a few billion light-years. The cosmic microwave background comes from a shell at a distance of 46 billion light-years, but it is a two-dimensional projection, and its information about our three-dimensional neighborhood is indirect. So when we ask whether we are in a special region, we are asking about a volume that is small compared to the observable universe, but still enormous by human standards, a volume containing hundreds of thousands of galaxies, a volume that would take light hundreds of millions of years to cross. To understand whether such a region could differ significantly from the cosmic average, we need to understand the origin of large-scale structure. In the standard cosmological model, structure grows from quantum fluctuations in the early universe, fluctuations that were stretched to macroscopic scales by cosmic inflation, a brief period of exponential expansion in the first fraction of a second after the Big Bang. These fluctuations were imprinted on the density of matter and radiation, and they evolved under gravity to form the galaxies and clusters we see today. The statistical properties of these fluctuations are predicted by inflation, and they match the observed properties of the cosmic microwave background remarkably well. But inflation does not predict that every region of the universe will have exactly the same properties. It predicts a statistical distribution, and different regions, if large enough, can deviate from the mean. The question is how large the deviations can be and how they affect observables. One way to quantify this is through the concept of the power spectrum, a mathematical description of how the amplitude of fluctuations depends on their scale. The power spectrum is measured from the cosmic microwave background and from large-scale structure surveys, and it is a key input to cosmological models. But the power spectrum is an average over many regions of space, and in any given region, the actual amplitude of fluctuations can differ from the average due to statistical noise. If our region happens to have slightly more or slightly less power on certain scales, this could affect our measurements of the Hubble constant, the growth rate of structure, and other quantities. The challenge is to determine whether the observed discrepancies are consistent with the expected level of statistical fluctuation or whether they require a more fundamental explanation. Let us consider a specific example. Suppose we are inside a spherical region, several 100 million light-years in radius, where the average density of matter is 10% lower than the cosmic mean. This underdensity would have several effects. First, the local expansion rate would be slightly higher because there is less gravitational pull to slow the expansion. Second, the growth rate of structure within the region would be slightly lower because there is less matter to clump together. Third, light traveling through the region from outside would be redshifted slightly differently than light traveling through an average region, affecting the distance redshift relation. All of these effects could, in principle, contribute to the observed tensions. The question is whether a single underdense region can explain all the tensions simultaneously or whether it creates new problems while solving old ones. One problem is that an underdense region large enough to affect the Hubble constant would also affect the observed distribution of galaxies. If we're near the center of a large void, then the density of galaxies around us should decrease systematically with distance up to the edge of the void and then increase again beyond the edge. This pattern should be detectable in redshift surveys, and while some studies have claimed to see evidence of such a pattern, others have not. The evidence is inconclusive, in part because the expected signal is subtle and in part because redshift surveys are limited by selection effects and by the finite volume they probe. Moreover, our peculiar velocity, the velocity of the Milky Way relative to the cosmic microwave background, is influenced by the gravitational pull of nearby large-scale structure. If we are in a large void, the void should leave a signature in our peculiar velocity, and this signature should be consistent with the observed dipole in the microwave background. Again, the evidence is ambiguous. Another problem is that the cosmic microwave background is sensitive to the properties of space along the entire line of sight from the surface of last scattering to us. If our local region differs significantly from the cosmic average, this could affect the observed pattern of fluctuations in the microwave background, but the effect is suppressed because the region is small compared to the total distance to the surface of last scattering. For a region several 100 million light-years across, the effect on the microwave background is expected to be small, on the order of 1% or less, which is difficult to detect given the intrinsic fluctuations in the microwave background and the noise in the measurements. Still, some researchers have searched for anomalies in the microwave background that could be attributed to a local void or other large-scale structure, and while a few tantalizing hints have been reported, none have been confirmed with high statistical significance. Let us now consider the possibility that the problem is not with our location, but with our understanding of the laws themselves. General relativity and quantum field theory are extraordinarily successful, but they are not complete. General relativity does not incorporate quantum mechanics, and quantum field theory does not incorporate gravity in a consistent way. The standard model of particle physics describes three of the four fundamental forces: electromagnetic, weak, and strong, but it does not include gravity, and it does not explain the nature of dark matter or dark energy. Dark matter, which makes up about 85% of the matter in the universe, has not been directly detected. Dark energy, which makes up about 70% of the total energy density of the universe, is even more mysterious. In the standard cosmological model, dark energy is represented by a cosmological constant, a term in Einstein's equations that corresponds to a constant energy density of empty space. But the cosmological constant has a value that is roughly 120 orders of magnitude smaller than what quantum field theory predicts, a discrepancy so enormous that it is called the cosmological constant problem. This suggests that our understanding of vacuum energy is fundamentally incomplete. If dark energy is not a cosmological constant, but a dynamical field, something that changes over time or varies from place to place, then the expansion history of the universe could be different from what the standard model predicts. A dynamical dark energy field could affect the expansion rate in a late universe without affecting the early universe, potentially resolving the Hubble tension. It could also affect the growth of structure, potentially resolving the S8 tension. Many models of dynamical dark energy have been proposed, with names like quintessence, quiescence, and coupled dark energy, and these models introduce new parameters that can be adjusted to fit the data. But so far, none of these models has been shown to resolve all the tensions without introducing new problems or requiring fine-tuning of parameters. Another possibility is that gravity itself behaves differently on large scales than general relativity predicts. General relativity has been tested extensively in the solar system, in binary pulsar systems, and in the recent detections of gravitational waves from merging black holes and neutron stars, and it has passed every test with flying colors. But these tests probe scales from kilometers to thousands of light years, while the tensions in cosmology emerge on scales of millions to billions of light years. On these larger scales, gravity might be modified in subtle ways that do not violate the existing tests, but do affect the expansion and growth of structure. Many modified gravity theories have been proposed, and some of them can alleviate the cosmological tensions, but they often predict other effects that have not been observed, such as deviations in gravitational lensing or in the propagation speed of gravitational waves. The constraints are tight, and the room for modification is narrow. A third possibility is that the standard model of particle physics is incomplete in ways that affect cosmology. For example, there might be additional light particles, particles with masses much smaller than the electron, that were produced in the early universe and that contribute to the energy density or affect the expansion rate. These particles are generically called dark radiation, and they are parameterized by a quantity called the effective number of neutrino species, which counts the number of particle species that behave like neutrinos in the early universe. The standard model predicts an effective number of 3.046, corresponding to the three known types of neutrinos, plus a small contribution from other processes. Measurements of the cosmic microwave background constrain the effective number to be close to 3, but there is some room for additional contributions. If there are additional light particles, they could affect the expansion rate in the early universe, changing the sound horizon, a key length scale that is imprinted in the cosmic microwave background and used to calibrate distance measurements. A change in the sound horizon could shift the inferred value of the Hubble constant, potentially resolving the tension. However, such a modification would also affect other observables, and it is not clear whether it can resolve the tension without creating new discrepancies. Let us return to the question of what it means for physics to add up. In a fundamental sense, physics adds up if the laws we have written down are complete, consistent, and universally applicable. Completeness means that the laws account for all observed phenomena. Consistency means that the laws do not contradict each other or lead to logical paradoxes. Universality means that the laws hold at all times and in all places, at least within the domain of validity of the theory. The standard model of particle physics and general relativity, combined into the lambda cold dark matter cosmological model, are remarkably complete and consistent within their domain. They explain the evolution of the universe from the first moments after the Big Bang to the present day, the formation of light elements in the first few minutes, the release of the cosmic microwave background, the formation of galaxies and large-scale structure, and the accelerated expansion of the universe in the recent past. But the tensions we have discussed suggest that this model is not fully complete, or that its domain of validity is more limited than we thought. If the model is incomplete, the incompleteness could take several forms. It could be that there are missing ingredients, new fields, or particles that have not yet been discovered. It could be that the existing ingredients have properties that we have not fully characterized, such as a time-varying or spatially varying dark energy density. It could be that the symmetries and conservation laws we assume are only approximate, holding on average, but not exactly in every region. Or it could be that the very concepts we use, such as a universal expansion rate or a single cosmic time, are idealizations that break down when we account for the full complexity of the universe. The universe is not a perfectly smooth, isotropic, homogeneous expanse. It is a dynamic, evolving structure, with matter clumped into galaxies and clusters, with voids in between, with gravitational waves rippling through space-time, with quantum fields fluctuating at every point. General relativity is a nonlinear theory, meaning that the effects of curvature and matter do not simply add up in a linear way. The presence of matter curves space-time, and the curvature affects the motion of matter, and this feedback can lead to effects that are not captured by simple averaging. When we speak of the expansion rate of the universe, we are implicitly averaging over all the inhomogeneities, treating the universe as though it were smooth on large scales. But the process of averaging is subtle, and there are different ways to do it, and they can give different answers. This is known as the averaging problem in cosmology, and it has been debated for decades. The averaging problem arises because the Einstein field equations are nonlinear. If we have a space-time that is inhomogeneous, with regions of high density and low density, and we want to describe its average behavior, we cannot simply average the density and plug it into the equations. We must solve the equations for the full, inhomogeneous space-time and then average the result, and this can give a different answer. The difference is called a back reaction, and it represents the effect of small-scale structure on large-scale dynamics. Some researchers have argued that back reaction could be large enough to affect the expansion rate and resolve the Hubble tension without invoking dark energy or modified gravity. Others have argued that back reaction is negligible in realistic cosmological models. The debate is technical and ongoing, and it hinges on how one defines averaging and what approximations are valid. One way to think about back reaction is to consider the energy density of the gravitational field itself. In general relativity, energy is not localized in the gravitational field in the same way it is localized in matter or radiation. There is no well-defined notion of gravitational energy density at a point. But gravitational waves carry energy, and the presence of structure in the universe generates tidal forces and shear, which are manifestations of space-time curvature. These effects could, in principle, contribute to the effective energy density on large scales, altering the expansion rate. Whether this contribution is large enough to matter is controversial, and it depends on the details of how structure is distributed and how the averaging is performed. Another subtle issue is the choice of gauge, the choice of coordinates or reference frame in which we describe the universe. General relativity is a gauge theory, meaning that the same physical situation can be described in many different coordinate systems, and the equations must be formulated in a way that is independent of this choice. But when we make measurements, we are implicitly choosing a gauge, a way of slicing space-time into space and time, and different choices can lead to different interpretations of the same data. For example, the Hubble constant is defined in a particular gauge, the gauge in which space-time is foliated into surfaces of constant cosmic time, and galaxies are assumed to move only due to the expansion of space, not due to peculiar velocities. But in reality, galaxies have peculiar velocities, and these velocities affect the observed redshifts. When we measure the Hubble constant from supernovae, we must correct for these peculiar velocities, and the correction depends on assumptions about the velocity field, which is not directly observable. Different assumptions can lead to different inferred values of the Hubble constant, and this is another potential source of systematic error. Let us now consider the possibility that the constants of nature are not truly constant. The speed of light, the gravitational constant, the fine structure constant, and other fundamental constants appear in the equations of physics, and we typically assume that they have the same value everywhere and at all times. But there is no deep theoretical reason why this must be true. In fact, in some extensions of the Standard Model, such as string theory, the values of these constants are determined by the configuration of extra dimensions or by the vacuum state of various fields, and these configurations could vary from place to place or change over time. If the constants of nature vary, even slightly, it could have profound effects on cosmology and astrophysics. The fine structure constant, which characterizes the strength of the electromagnetic interaction, has been the subject of particularly intense scrutiny. Measurements of light from distant quasars, light that was emitted billions of years ago and has traveled through the universe to reach us, can be used to test whether the fine structure constant was the same in the distant past as it is today. The method relies on the fact that the wavelengths of spectral lines from atoms and molecules depend on the fine structure constant, and by comparing the observed wavelengths to the expected wavelengths, one can infer whether the constant has changed. Some studies have claimed to detect small variations in the fine structure constant at the level of a few parts per million, with the constant being slightly different in different directions on the sky. Other studies have found no significant variation. The claimed variations are controversial, and they are at the edge of what current measurements can reliably detect. But if they are real, they would imply that the laws of physics are not exactly the same everywhere, that we are in a region where the fine structure constant has a particular value, and that value differs from the value in other regions. A varying fine structure constant would have implications for the interpretation of cosmological observations. For example, the sound horizon, the distance that sound waves could travel in the early universe before the cosmic microwave background was released, depends on the speed of sound in the primordial plasma, and the speed of sound depends on the ratio of radiation pressure to energy density, which in turn depends on the fine structure constant. If the fine structure constant was different in the early universe, the sound horizon would be different, and this would affect the calibration of the cosmic distance ladder and the inferred value of the Hubble constant. Similarly, the recombination history, the process by which electrons and protons combine to form neutral hydrogen and release the microwave background, depends on the binding energy of hydrogen, which depends on the fine structure constant. A variation in the fine structure constant would shift the time of recombination and alter the pattern of fluctuations in the microwave background. Even if the constants of nature do not vary in time, they could vary in space, a possibility that is even more radical. If the fine structure constant has different values in different regions of the universe, then the properties of atoms, the spectra of stars, the structure of galaxies, everything would depend on location. Our region would have one value, and other regions would have other values, and the boundary between regions would be a place where the laws of physics, as we formulate them, would not apply in the usual way. This is speculative, and there is no direct evidence for spatial variation, but it is not ruled out by current observations, especially if the scale of variation is larger than the observable universe. There is also the question of what we mean by a region. Space is continuous, not discrete, and any talk of a region is an approximation, a way of dividing space into parts for the purpose of analysis. But the universe does not come with natural boundaries. The edges of structures, the boundaries between voids and filaments, are gradual transitions, not sharp lines. When we say that we might be in a special region, we are implicitly defining that region by some property, such as the average density or the expansion rate, and asking whether that property differs significantly from the cosmic mean. But the answer depends on how we define the region, how we draw the boundary, and what volume we average over. If we make the region larger, the difference from the cosmic mean becomes smaller because we are averaging over more fluctuations. If we make the region smaller, the difference can become larger, but the region becomes less representative. There is a scale at which the universe transitions from inhomogeneous to homogeneous, and that scale is estimated to be around a few 100 million light years. But the transition is not sharp, and the exact value depends on the observable being considered. Let us think about the implications of being in a region where the local expansion rate is higher than the cosmic average. If this is the case, then our measurements of the Hubble constant are biased, and the true value, the value that would be measured by an observer in an average region, is lower. This would mean that the age of the universe, as inferred from the Hubble constant, is older than we currently estimate. It would mean that the distances to faraway galaxies, as inferred from their redshifts, are different from what we calculate. It would mean that the history of cosmic expansion is not what we think it is. All of our cosmological conclusions are based on the assumption that we are in a typical location, and if that assumption is wrong, then many of those conclusions must be revised. But there is a deeper issue. If we are in a special region, how do we know that the laws of physics we have inferred from local measurements apply everywhere? Our knowledge of physics comes from experiments and observations made here, in our solar system, in our galaxy, in our local group of galaxies. We assume that the same laws apply throughout the universe because we see the same patterns, the same spectral lines from atoms, the same behavior of light and gravity. But if the region we observe is not typical, then the laws we have inferred might not be universal. They might be effective laws, laws that describe the behavior of matter and energy in our particular environment, but not in other environments. This is not to say that the fundamental laws change, but that the effective parameters, the masses of particles, the strengths of interactions, the properties of the vacuum, could depend on the local environment in ways we do not fully understand. This brings us to the concept of the multiverse, the idea that our universe is just one of many, each with different properties, different laws, or different values of the constants of nature. In some versions of the multiverse, the different universes are causally disconnected, separated by vast expanses of space that are expanding so fast that light will never travel between them. In other versions, the different universes are different regions of a single space-time, regions that underwent different histories of phase transitions or symmetry breaking, leading to different effective laws. If the multiverse is real, and if our universe is just one region within it, then the question of whether we are in a special region becomes a question of whether our region is typical within the multiverse. And the cosmological principle must be reformulated as a principle that applies not to space within our universe, but to the ensemble of all universes. The multiverse is controversial. It is difficult to test because, by definition, we cannot observe other universes. Some physicists argue that it is not science because it does not make falsifiable predictions. Others argue that it is a natural consequence of inflation and string theory, and that it provides an explanation for the observed values of the constants of nature, which would otherwise seem fine-tuned for the existence of life. The fine-tuning argument goes as follows. If the cosmological constant were much larger, the universe would have expanded too quickly for galaxies to form. If it were much smaller or negative, the universe would have recollapsed before stars could form. If the fine structure constant were slightly different, the chemistry of carbon and oxygen would be different, and life, as we know it, could not exist. The values of the constants seem to lie in a narrow range that permits the existence of complex structures and life, and this seems unlikely to be a coincidence. The multiverse offers an explanation. If there are many universes with different values of the constants, then it is not surprising that we find ourselves in one where the constants permit our existence, because we could not exist in the others. This is called the anthropic principle, and it is deeply controversial because it shifts the explanation from physics to selection effects, from why the constants have the values they do to why we observe the values we do. Let us set aside the multiverse for now and return to the specific question of our region. Whether or not there are other universes, there's still the question of whether our region of this universe is typical. To answer this question, we need to measure the properties of a universe on scales larger than our local neighborhood, and we need to compare those properties to what we measure locally. This is difficult because the farther we look, the farther back in time we see, and the properties of the universe have changed over time due to expansion and the evolution of structure. When we observe a galaxy 10 billion light-years away, we are seeing it as it was 10 billion years ago, when the universe was younger, denser, and hotter. To compare the properties of distant regions to local regions, we must account for this evolution, and this requires a model of how the universe evolves, which brings us back to the standard cosmological model and the assumption that the model applies everywhere. This is a kind of circularity. We use the model to interpret the observations, but the observations are what we use to test the model. If the model is wrong, or if it does not apply everywhere, then our interpretation of the distant observations could be incorrect, and our conclusion about whether we are in a typical region could be biased. Breaking this circularity requires model-independent tests, measurements that do not rely on assumptions about the expansion history or the growth of structure. Such tests are difficult, but they exist. One example is the measurement of the geometry of space, which can be inferred from the statistics of the cosmic microwave background and from the large-scale distribution of galaxies. If space is flat, as the standard model predicts, then the angles and distances we measure should satisfy certain geometric relations, and these relations can be tested without assuming a specific expansion history. So far, measurements indicate that space is flat to within about 1%, which is consistent with the standard model, but does not rule out small deviations. Another example is the measurement of the matter-power spectrum, the statistical distribution of matter on different scales, which can be inferred from galaxy surveys and gravitational lensing. The shape of the power spectrum depends on the initial conditions set by inflation and on the physics of the early universe, and it is less sensitive to the recent expansion history than measurements of distances or the Hubble constant. If the power spectrum measured locally differs from the power spectrum measured in distant regions, this would be evidence that our region is not typical. Some studies have claimed to detect differences in the power spectrum on very large scales comparable to the size of the observable universe. But these claims are contentious and difficult to verify because the number of independent measurements on such large scales is small and the statistical uncertainties are large. There's also the question of the isotropy of the universe, whether it looks the same in all directions. The cosmological principle asserts that the universe is isotropic, at least on large scales, but there are some observations that suggest small deviations from isotropy. One is the dipole in the cosmic microwave background, which is interpreted as our motion through the rest frame of the microwave background at a speed of about 370 kilometers per second. This dipole is expected and well understood, but there are also claims of higher-order anisotropies, such as a preferred direction in the distribution of galaxy clusters or in the polarization of light from distant quasars. These claims are controversial, and many of them have not been confirmed by independent observations. But if they are real, they would suggest that the universe is not perfectly isotropic, and that there are large-scale structures or flows that break the symmetry assumed by the cosmological principle. An anisotropic universe would have profound implications. It would mean that the expansion rate is different in different directions, that the properties of space depend on direction as well as location, and that the simple Friedmann-Robertson-Walker metric, the mathematical description of a homogeneous and isotropic universe, does not apply. It would complicate the interpretation of observations, because the redshift of a galaxy would depend not only on its distance, but also on the direction in which we observe it. It would raise questions about the origin of the anisotropy, whether it is a relic of the early universe or a consequence of large-scale structure, and it would challenge the notion that the universe can be described by a single cosmic time and a single expansion rate. Let us consider now the role of dark matter in determining whether our region is special. Dark matter makes up most of the matter in the universe, and its distribution determines the gravitational potential, which in turn determines the motion of galaxies and the growth of structure. if the density of dark matter in our region is higher or lower than the cosmic average. This would affect the local expansion rate and the local growth rate of structure. The question is whether we can measure the local density of dark matter directly, without relying on cosmological models. One way to measure the density of dark matter is through gravitational lensing, the bending of light by gravity. The amount of bending depends on the total mass along the line of sight, including dark matter, and by observing how the images of distant galaxies are distorted by foreground structures, we can infer the distribution of dark matter. Lensing measurements on small scales, within galaxies and clusters, have provided strong evidence for the existence of dark matter and have measured its distribution with some precision. Lensing measurements on large scales, where the lensing signal is weak and must be extracted statistically from large samples of galaxies, provide information about the total amount of matter in the universe and its distribution on scales of tens to hundreds of millions of light-years. These measurements are consistent with the Standard Model, but they have large uncertainties, and they do not yet provide a definitive answer to whether our local region has a typical density of dark matter. Another way to measure the density of dark matter is through the dynamics of galaxies and clusters. The velocities of stars within galaxies and the velocities of galaxies within clusters are determined by the gravitational pull of the total mass, including dark matter. By measuring these velocities, we can infer the mass distribution. This method has been used for decades and has provided some of the earliest evidence for dark matter. But it is subject to uncertainties because the relationship between the observed velocities and the underlying mass distribution depends on assumptions about the orbits of stars and galaxies, about whether the system is in equilibrium, and about whether the gravitational potential is static or changing over time. Different assumptions can lead to different estimates of the mass, and there is ongoing debate about the details. There is also the question of the nature of dark matter itself. The standard assumption is that dark matter consists of particles that interact only through gravity and possibly through the weak nuclear force, particles called weakly interacting massive particles, or WIMPs. Despite decades of experimental searches, WIMPs have not been detected directly, and this has led to the exploration of alternative candidates, such as axions, sterile neutrinos, and primordial black holes. Different types of dark matter could have different effects on the formation and evolution of structure, and if the dark matter in our region is different from the dark matter elsewhere, this could be another way in which our region is special. However, there is currently no evidence that the nature of dark matter varies from place to place, and most theoretical models assume that it is uniform throughout the universe. Let's turn now to the role of dark energy. Dark energy is the dominant component of the energy density of the universe today, making up about 70% of the total. In the Standard Model, dark energy is represented by a cosmological constant, a constant energy density of empty space that does not change over time or vary from place to place. The cosmological constant drives the accelerated expansion of the universe, and it is required to explain the observed brightness of distant supernovae. But as mentioned earlier, the value of the cosmological constant is much smaller than what quantum field theory predicts, and this has led to speculation that dark energy is not a cosmological constant, but something more complicated. If dark energy is dynamical, if it can change over time or vary in space, then the expansion history of the universe could be different from what the Standard Model predicts, and our local measurements could be biased if the local value of dark energy is different from the cosmic average. Many models of dynamical dark energy have been proposed, and they can be broadly classified into two categories. Quintessence models, where dark energy is a slowly rolling scalar field, and models with interactions, where dark energy interacts with dark matter or with ordinary matter. Quintessence models can lead to a time-varying expansion rate, and interaction models can lead to spatial variations in dark energy density. Both types of models can, in principle, alleviate the Hubble tension, but they must also satisfy other constraints, such as constraint from the growth of structure, from the cosmic microwave background, and from tests of general relativity. One specific model that has received attention is the locally varying dark energy model, where the dark energy density has a spatial gradient on scales of hundreds of millions of light-years. If we're located in a region where the dark energy density is lower than the cosmic average, the local expansion rate would be lower, which would exacerbate rather than resolve the Hubble tension. But if we are in a region where the dark energy density is higher, the local expansion rate would be higher, which could help resolve the tension. The challenge is to construct a model where the spatial variation is large enough to explain the observations, but not so large that it violates other constraints, such as the isotropy of the cosmic microwave background or the observed distribution of large-scale structure. Most attempts to build such models have found that the required variation is larger than what can be easily accommodated within standard field theory, but the exploration continues. Another possibility is that dark energy is not a new field or a cosmological constant, but an effective description of the backreaction of structure on the expansion, as mentioned earlier. In this view, the accelerated expansion is not caused by a mysterious new component of energy, but by the failure of the simple Friedmann equations to accurately describe a universe with significant inhomogeneity. This is an attractive idea because it does not require new physics, only a more careful treatment of the known physics. But as noted earlier, the magnitude of backreaction is controversial, and most calculations suggest that it is too small to account for the observed acceleration. Nevertheless, the debate is ongoing, and it highlights the fact that our understanding of how to connect the local, inhomogeneous universe to the global, average description is still incomplete. Let us consider now the observational evidence more carefully. The Hubble tension is based on two primary classes of measurements. Measurements from the early universe, particularly the cosmic microwave background, and measurements from the late universe, particularly supernovae. The early universe measurements rely on the standard model of cosmology and on the assumption that the properties of the universe at the time the microwave background was released can be extrapolated to the present using general relativity and the known physics of matter and radiation. The late universe measurements rely on a series of steps in the cosmic distance ladder, a chain of methods that build on each other to measure distances to faraway galaxies. Each step in the ladder has uncertainties, and the uncertainties accumulate as we go to larger distances. The first step in the cosmic distance ladder is the measurement of distances within our own galaxy using parallax. The apparent shift in the position of nearby stars as the Earth orbits the Sun parallax measurements are direct and geometric, and they provide a solid foundation for the distance ladder. The second step is the use of Cepheid variable stars, stars whose brightness varies periodically in a way that is correlated with their intrinsic luminosity. By measuring the period of a Cepheid, we can infer its luminosity, and by comparing the luminosity to the observed brightness, we can calculate the distance. Cepheids are bright enough to be seen in nearby galaxies, and they have been used to calibrate the distances to galaxies that host supernovae. The third step is the use of type I supernovae. Stellar explosions are thought to have a standard intrinsic brightness, or at least a brightness that can be standardized using correlations between the brightness, the color, and the rate at which the supernova fades. By measuring the observed brightness of a type I supernova and comparing it to its intrinsic brightness, we can calculate the distance to its host galaxy. Each of these steps has potential sources of systematic error. Parallax measurements are limited by the precision of the observations and by the effects of the motion of the Sun and the stars. Cepheid measurements are affected by dust, which can absorb and redden the light, by the crowding of stars in distant galaxies, which can contaminate the measurements, and by the metallicity of the stars, which affects the period luminosity relation. Supernova measurements are affected by dust, by variations in the intrinsic brightness, and by the properties of the host galaxies. Many of these effects have been studied in detail, and corrections have been developed, but there is always the possibility of unrecognized biases, subtle effects that have not been fully accounted for. The fact that the Hubble tension persists across multiple independent teams and multiple refinements of the analysis suggests that any unrecognized systematic error would have to be present in all the measurements, which seems unlikely but not impossible. The early universe measurements, on the other hand, rely on a single snapshot of the universe at one time, and they require a model to extrapolate from that time to the present. The model includes the density of matter, the density of dark energy, the density of radiation, the curvature of space, and other parameters. The fit of the model to the observed pattern of fluctuations in the cosmic microwave background is remarkably good, with a chi-squared per degree of freedom close to 1, indicating that the model describes the data very well. But the model is based on assumptions, and if any of those assumptions are wrong, the inferred value of the Hubble constant could be biased. For example, the model assumes that the physics of the early universe is described by the standard model of particle physics, that there are no additional light particles beyond the known neutrinos, that the recombination history followed the expected path, and that the fluctuations are purely adiabatic, meaning that the ratios of different types of matter and radiation are the same everywhere. If any of these assumptions are violated, the inferred Hubble constant could change. One particularly important assumption is the value of the sound horizon, the distance that sound waves traveled in the primordial plasma before recombination. The sound horizon sets the scale of the acoustic peaks in the power spectrum of the microwave background, and it is used as a standard ruler to measure distances. The sound horizon depends on the expansion rate in the early universe, which depends on the densities of matter and radiation and on any additional contributions to the energy density, such as dark radiation. If there is additional dark radiation, the sound horizon would be smaller, and the inferred value of the Hubble constant would be higher, potentially resolving the tension. But the amount of dark radiation that would be required is in tension with other measurements, such as measurements of the abundance of light elements produced in Big Bang nucleosynthesis, which depend on the expansion rate at the time when nucleosynthesis occurred. This creates a new tension, and it is not clear that adding dark radiation resolves more problems than it creates. Another assumption is that the fluctuations in the microwave background are Gaussian, meaning that their statistical properties are fully described by the power spectrum and that there are no higher-order correlations. The standard inflationary models predict Gaussian fluctuations to a very good approximation, and tests of non-Gaussianity have found no significant deviations. But if the fluctuations are non-Gaussian, this could affect the inferred cosmological parameters in subtle ways. Similarly, the model assumes that the fluctuations are isotropic, that they have the same statistical properties in all directions. As mentioned earlier, there are some claims of anisotropy in the microwave background, and if these are real, they could affect the inferred Hubble constant. However, the claimed anisotropies are small and controversial, and most analyses treat the fluctuations as isotropic. There is also the question of foreground contamination. The cosmic microwave background is observed through our galaxy and through the intergalactic medium, and both of these can emit or scatter radiation that contaminates the signal. Our galaxy emits synchrotron radiation from relativistic electrons spiraling in magnetic fields, free radiation from electrons scattering off ions, and thermal emission from dust. The intergalactic medium contains hot gas in galaxy clusters, and this gas can scatter microwave background photons through the Sunyaev-Zeldovich effect, shifting their energies and distorting the observed spectrum. All of these foregrounds must be carefully modeled and subtracted, and any errors in the modeling could bias the inferred cosmological parameters. The Planck satellite, which made the most precise measurements of the microwave background to date, included multiple frequency channels to separate the foregrounds from the cosmological signal, and extensive tests were performed to ensure that the foreground subtraction was accurate. But there is always some residual uncertainty, and it is possible that small, unrecognized foreground contamination could affect the results. Let us now turn to the question of what observations could definitively determine whether we are in a special region. One approach is to measure the Hubble constant using methods that are independent of the cosmic distance ladder and that probe different ranges of distance and redshift. One such method is the use of gravitational lensing time delays. When light from a distant quasar is lensed by a foreground galaxy, multiple images of the quasar are produced, and these images follow different paths through the gravitational field of the lens. If the quasar's brightness varies, the variations are seen in the different images at different times, because the light travel time along each path is different. By measuring the time delays between the images and modeling the mass distribution of the lens, the distance to the lens and to the quasar can be inferred, and from this, the Hubble constant can be determined. This method is independent of Cepheids and supernovae, and it probes intermediate distances between the local measurements and the cosmic microwave background. So far, measurements of the Hubble constant from time delay lenses have yielded values that are closer to the local measurements than to the early universe measurements, supporting the existence of the tension, but the uncertainties are still relatively large, and more data are needed. Another method is the use of gravitational waves from merging neutron stars. When two neutron stars merge, they emit gravitational waves that can be detected by observatories like LIGO and Virgo, and they also emit light, a kilonova, that can be detected by telescopes. By measuring the gravitational wave signal, the distance to the merger can be inferred, and by measuring the redshift of the host galaxy, the Hubble constant can be determined. This method is independent of the cosmic distance ladder and does not rely on any standard candles, but it requires the detection of mergers that are close enough to measure the gravitational waves and far enough to be in the Hubble flow, and it requires an accurate measurement of the host galaxy's redshift. So far, only a few such events have been detected, and the inferred Hubble constant has large uncertainties. But as more events are detected, this method will become increasingly powerful. A third method is the use of the tip of the red giant branch, a feature in the luminosity function of stars that can be used as a distance indicator. Red giant branch stars are evolved stars that have exhausted the hydrogen in their cores and are burning hydrogen in a shell around the core. As they evolve, they reach a maximum luminosity, the tip of the red giant branch, before they ignite helium in their cores. The luminosity of the tip is relatively insensitive to the metallicity and age of the stars, and it can be calibrated using stars in our galaxy and in nearby galaxies where distances are known from other methods. The tip of the red giant branch has been used to measure distances to galaxies in the local universe, and the inferred Hubble constant is intermediate between the early and late universe values, though closer to the late universe value. This method is independent of Cepheids, though it still relies on parallax measurements for calibration, and it provides another check on the cosmic distance ladder. Each of these methods has its own systematics, and none is free from assumptions. But the fact that multiple independent methods yield results that are broadly consistent with each other and that are discrepant with the early universe value strengthens the case that the Hubble tension is real and not due to a single unrecognized systematic error. It also makes the hypothesis of a local void or other special region less attractive, because such a hypothesis would have to explain why all the late universe methods are biased in the same way, even though they probe different distance ranges and rely on different physical processes. Let us consider the implications of the S8 tension, the discrepancy in the amplitude of matter fluctuations. As with the Hubble tension, the S8 tension could be due to systematic errors, to new physics, or to cosmic variance. Measurements of S8 from weak lensing surveys are challenging because the lensing signal is small, and it must be extracted from the shapes of millions of galaxies, each of which has an intrinsic shape that is not due to lensing. The intrinsic shapes must be averaged out statistically, and any correlation in the intrinsic shapes, due for example to the tidal fields of nearby galaxies or to galaxy alignments along filaments, could bias the lensing signal. This is called intrinsic alignment, and it is one of the main systematic effects in weak lensing surveys. Extensive simulations and tests have been performed to understand and correct for intrinsic alignments, but uncertainties remain. Another systematic effect in weak lensing is the contamination of the photometric redshifts, the estimates of galaxy distances based on their colors in multiple filters. Weak lensing surveys measure the shapes and colors of galaxies, and the colors are used to estimate the redshifts. Errors in the photometric redshifts can bias the inferred amplitude of fluctuations because the lensing signal depends on the distances to the galaxies. Photometric redshifts are calibrated using spectroscopic redshifts for a subset of galaxies, but the calibration sample may not be representative of the full sample, and this can introduce biases. Extensive efforts have been made to improve photometric redshift calibration, but it remains a significant source of uncertainty. Measurements of S8 from galaxy clustering also have systematics. The relationship between the distribution of galaxies and the distribution of dark matter is not one-to-one. Galaxies are biased tracers of the dark matter, meaning that they preferentially form in regions where the dark matter density is higher, and the strength of this bias depends on the properties of the galaxies, such as their mass and color. The bias must be modeled, and different models can give different results. Moreover, the clustering signal is affected by redshift space distortions, the apparent clustering along the line of sight, due to the peculiar velocities of galaxies. These distortions contain information about the growth rate of structure, but they also complicate the interpretation of the clustering signal, and they must be carefully modeled. Despite these challenges, multiple independent weak lensing surveys and galaxy clustering surveys have measured S8, and the results are broadly consistent with each other and discrepant with the value inferred from the cosmic microwave background. As with the Hubble tension, this suggests that the S8 tension is real, though the statistical significance is lower, and the possibility of systematic errors cannot be ruled out. If the tension is real, it could indicate that the growth of structure is slower than predicted, which could be due to dynamical dark energy, modified gravity, or a local underdensity. A local underdensity would affect both the expansion rate and the growth rate, potentially explaining both the Hubble tension and the S8 tension simultaneously. But as discussed earlier, the constraint from large-scale structure surveys and for the cosmic microwave background make this explanation difficult to reconcile with all the data. Let's now think about the deeper question of what it means for a region to be atypical. In statistical mechanics, the properties of a system are determined by averaging over a large number of microstates, each of which is equally probable in equilibrium. The macroscopic properties, such as temperature and pressure, are emergent properties that arise from the statistical behavior of the microstates. But in a finite system, or in a system observed for a finite time, fluctuations occur, and the observed properties can deviate from the average. The probability of a fluctuation decreases exponentially with its magnitude. So large fluctuations are rare, but they're not impossible. In cosmology, the universe is a single realization, a single draw from the probability distribution, and we cannot perform ensemble averages over many universes. We can only average over different regions of space, and even this is limited by the finite speed of light and the age of the universe. If our region is a rare fluctuation, a statistical outlier, then our observations would not be representative of the universe as a whole, and the cosmological principle would be violated. The question is how rare a fluctuation we are willing to accept. If the probability of our region being as atypical as the data suggest is 1 in 10, this might be acceptable as a statistical fluke. If the probability is 1 in 1,000, it becomes less comfortable. If the probability is 1 in 1,000,000, it strains credibility, and we begin to suspect that either the data are wrong or the model is incomplete. The probabilities depend on the assumed model, on the power spectrum of fluctuations, and the volume over which we average, and they're not easy to calculate precisely. But rough estimates suggest that the Hubble tension and the S8 tension, if attributed to cosmic variance, would require us to be in a region that is a few standard deviations from a mean, which is unlikely but not impossible. There is also the question of selection effects. If the formation of observers of intelligent life requires certain conditions, such as a certain density of matter or a certain expansion rate, then we should not expect to find ourselves in a typical region, but in a region where those conditions are met. This is the weak anthropic principle, the idea that our observations are conditioned on our existence. If the conditions for life are rare, occurring only in certain types of regions, then it is not surprising that we find ourselves in such a region, even if it is atypical in other respects. The challenge is to formalize this argument, to calculate the probability that observers would find themselves in a region with the properties we observe, given the distribution of regions in the universe and the conditions required for life. This is a difficult problem, and it involves many assumptions about the nature of life and the factors that determine where it can arise. Let us now consider the role of quantum mechanics in determining the properties of our region. Quantum mechanics introduces fundamental uncertainty into the initial conditions of the universe. In the early universe, during inflation, quantum fluctuations in the inflaton field were stretched to macroscopic scales and became the seeds of the density fluctuations we observe today. These fluctuations are inherently random, governed by the probabilities of quantum mechanics, and they determine the large-scale structure of the universe. Different regions of space, even if they started with the same laws of physics and the same values of the constants, would have different realizations of the quantum fluctuations, and thus different large-scale structures, different expansion rates, and different properties. In this sense, every region is unique, and the question is not whether our region is special, but whether it is so special that it cannot be explained by quantum randomness alone. Quantum mechanics also introduces the possibility of quantum branching, the idea that the universe continuously splits into multiple branches, each representing a different outcome of a quantum measurement. In the many-worlds interpretation of quantum mechanics, every quantum event produces a superposition of outcomes, and each outcome exists in a separate branch of the wave function. If this interpretation is correct, then there are many versions of our region, each with slightly different properties, corresponding to different outcomes of the quantum fluctuations in the early universe. In this view, the question of whether we are in a special region becomes a question of measure, of how to count the different branches and determine the probability of finding ourselves in a branch with the properties we observe. This is a deep and unresolved problem in quantum cosmology, and it connects to the foundations of quantum mechanics and the nature of probability. Another aspect of quantum mechanics that is relevant here is the concept of the quantum vacuum. In quantum field theory, the vacuum is not empty but filled with fluctuating fields, virtual particles that pop in and out of existence on timescales determined by the uncertainty principle. The energy density of the vacuum, the cosmological constant, is related to the properties of these fluctuations, though as mentioned earlier, the theoretical prediction is many orders of magnitude larger than the observed value. If the properties of the vacuum vary from place to place due to different configurations of fields or different vacuum states, then the cosmological constant would vary, and this could affect the expansion rate and the growth of structure. This is the idea behind the string landscape, the proposal that string theory admits a vast number of different vacuum states, each with different values of the constants of nature, and that our universe occupies one of these states. In this view, the question of why the constants have the values they do is answered by anthropic selection. We observe the values we do because only in regions with these values can observers exist. The string landscape is speculative, and it is based on theoretical developments in string theory that are not yet fully understood. String theory is an attempt to unify general relativity and quantum mechanics, to describe gravity as a quantum field theory, and it posits that the fundamental constituents of the universe are not point particles, but one-dimensional strings. The vibrational modes of the strings correspond to different particles, and the properties of the particles depend on the compactification of extra dimensions, dimensions beyond the three spatial dimensions we observe. Different ways of compactifying the extra dimensions lead to different vacuum states, different effective constants, and thus a landscape of possible universes. If this picture is correct, then the question of whether we are in a special region becomes a question of where we are in the landscape, and the answer depends on the dynamics of how the universe transitions from one vacuum state to another. Let us return to the specific question of the Hubble tension and the S8 tension and ask what kinds of observations could distinguish between the different explanations. If the tensions are due to systematic errors, then refining the measurements and reducing the uncertainties should eventually lead to convergence. If the tensions are due to new physics, such as dynamical dark energy or modified gravity, then other observables should also show deviations from the standard model, and these deviations should be consistent with the same new physics. If the tensions are due to our being in a special region, then measurements at different distances and in different directions should show variations that are consistent with the properties of that region. For example, if we are in a large void, the Hubble constant should increase with distance as we probe regions beyond the void, and the amplitude of fluctuations should increase as well. If we are in a region with varying dark energy, the equation of state of dark energy, The ratio of its pressure to its energy density should vary in a way that correlates with the local density and expansion rate. Future observations will be critical in testing these scenarios. The James Webb Space Telescope, with its increased sensitivity and resolution, is measuring Cepheids in more distant galaxies, extending the distance ladder and reducing the uncertainties. The Euclid mission and the Vera-Rubin Observatory will survey billions of galaxies, measuring their positions, shapes, and colors, and providing much more precise measurements of the large-scale structure and the growth rate of fluctuations. Gravitational wave observatories, as they detect more neutron star mergers, will provide independent measurements of the Hubble constant. The Simons Observatory and next-generation experiments will measure the cosmic microwave background with even higher precision, probing smaller scales and testing for deviations from the standard model. All of these observations will converge to either confirm the tensions, in which case new physics or a special location must be invoked, or resolve them, in which case the standard model will be vindicated and the tensions will be understood as the result of systematic errors. There's another possibility that we have not yet fully explored, which is that the concept of a single Hubble constant or a single expansion rate is an oversimplification. In a universe with significant inhomogeneity, different observers, located in different regions, would measure different expansion rates, and there would be no single, universal Hubble constant. The expansion rate would be an observer-dependent quantity like the velocity in special relativity, and what we call the Hubble constant would be the local expansion rate in our neighborhood. In this view, the Hubble tension would not be a tension at all, but a recognition that the universe does not expand uniformly, and that measurements made in different regions or using different methods probe different aspects of the expansion. This is related to the averaging problem mentioned earlier, and it raises deep questions about how to define cosmological observables in an inhomogeneous universe. To make this concrete, consider two observers, one located in a high-density region and one in a low-density region. The observer in the high-density region would experience a stronger gravitational pull, and the local expansion rate would be slower. The observer in the low-density region would experience a weaker gravitational pull, and the local expansion rate would be faster. If we ask what the Hubble constant is, the answer depends on which observer we ask. In general relativity, there is no preferred observer, no absolute frame of reference, and so there is no single objective answer. The Hubble constant, like many other quantities in general relativity, is a gauge-dependent quantity, and its value depends on the choice of coordinates and the choice of how to slice space-time into space and time. Different choices lead to different values, and the challenge is to find a choice that is physically meaningful and that can be related to observations. One proposal is to define the Hubble constant as the expansion rate in the frame in which the cosmic microwave background is at rest, the frame in which the dipole in the microwave background vanishes. This is a natural choice because the microwave background provides a preferred frame, a kind of cosmic reference frame, and it is the frame in which the universe looks most isotropic. But even in this frame, the expansion rate can vary from place to place if the density varies, and so the Hubble constant would still be a function of location. Another proposal is to define the Hubble constant as the average expansion rate over some large volume, large enough that the inhomogeneities average out. But the average depends on the size and shape of the volume, and different choices lead to different values. There is no unique way to define the average, and this ambiguity is at the heart of the averaging problem. Let's think about what it would mean observationally if the expansion rate varies from place to place. If we measure the redshift and distance of a galaxy, the redshift tells us how much the universe has expanded since the light was emitted, and the distance tells us how far the light has traveled. The relationship between redshift and distance depends on the expansion history, on how the expansion rate has changed over time. If the expansion rate also varies spatially, then the relationship between redshift and distance would depend on the path the light has taken, on whether it has passed through high-density or low-density regions. This would introduce scatter in the Hubble diagram, the plot of distance versus redshift, beyond what is expected from measurement errors and peculiar velocities. Some studies have looked for such scatter and have found hints of it, but the signal is small and difficult to disentangle from other effects. Another consequence of spatially varying expansion is that the cosmic microwave background would not be perfectly isotropic. Photons traveling from the surface of last scattering to us pass through regions with different densities and different expansion rates, and these variations would leave imprints on the observed temperature and polarization of the microwave background. The integrated Sachs-Wolf effect, mentioned earlier, is one such imprint, but there are others, such as the Ricciama effect, which is the time-dependent version of the integrated Sachs-Wolf effect, and the lensing of the microwave background by large-scale structure. All of these effects have been observed, and they are consistent with the standard model, but they are small, and it is difficult to detect deviations that would indicate a significant departure from homogeneity. There's also the question of how the inhomogeneity of a universe affects the interpretation of the cosmic microwave background itself. The microwave background is a two-dimensional projection of a three-dimensional universe, and the observed pattern of fluctuations is an integral over the line of sight from the surface of last scattering to us. If the universe is inhomogeneous, this integral is affected by the structure along the line of sight, and the inferred cosmological parameters could be biased. This effect is called the lensing of the microwave background, and it has been measured and corrected for in recent analyses. But the corrections are based on models of the large-scale structure, and if the models are wrong, the corrections could be wrong as well. Let us now consider the possibility that our understanding of the early universe is incomplete. The standard model of the early universe, based on the Big Bang and inflation, makes specific predictions about the properties of the cosmic microwave background, the abundance of light elements, and the formation of structure. These predictions have been tested extensively and have been confirmed to a remarkable degree. But there are aspects of the early universe that are not well understood, and it is possible that our ignorance of these aspects biases our interpretation of the observations. One example is the nature of inflation itself. Inflation is a period of exponential expansion that is thought to have occurred in the first fraction of a second after the Big Bang, and it is invoked to explain the homogeneity and isotropy of the universe, the flatness of space, and the origin of density fluctuations. But the mechanism that drives inflation, the inflaton field, is not part of the standard model of particle physics, and its properties are not well constrained. There are many different models of inflation with different potential energy functions for the inflaton, and these models make different predictions for the statistical properties of the fluctuations, such as the spectral index, the running of the spectral index, and the amplitude of gravitational waves. The observations constrain some of these properties, but they do not uniquely determine the model of inflation. If the true model of inflation is different from the models we have been considering, the inferred cosmological parameters, including the Hubble constant, could be different. Another example is the reheating period, the transition from inflation to the radiation-dominated era. At the end of inflation, the energy stored in the inflaton field is converted into particles, and the universe becomes hot and dense, filled with radiation and matter. The details of this transition depend on the couplings of the inflaton to other fields, and these couplings are not well known. If the reheating period was longer or shorter than assumed, or if it involved additional particles or interactions, this could affect the expansion history and the initial conditions for Big Bang nucleosynthesis, potentially changing the inferred Hubble constant. A third example is the possibility of phase transitions in the early universe. As the universe cooled, various fields underwent phase transitions, changes in their vacuum state, and these transitions could have affected the expansion rate and the properties of the primordial plasma. The electroweak phase transition, when the Higgs field acquired a non-zero expectation value and gave mass to the W and Z bosons and to the quarks and leptons, is one such transition. The QCD phase transition, when quarks and gluons confined into protons and neutrons, is another. Both of these transitions are predicted by the standard model of particle physics, and their effects on the expansion history are small and well understood. But there could be additional phase transitions associated with new physics beyond the standard model, and these could have larger effects. Let us turn to the question of whether the fundamental constants themselves could vary with time. If the speed of light, the gravitational constant, or the fine structure constant were different in the past, this would affect the expansion history, the evolution of structure, and the interpretation of observations. The constancy of the constants is an assumption, not a proven fact, and it is worth testing. As mentioned earlier, measurements of light from distant quasars have been used to test whether the fine structure constant has changed over time, with some studies claiming small variations and others finding no significant change. Similar tests have been performed for the gravitational constant, using observations of the orbits of planets, the dynamics of binary pulsars, and the nucleosynthesis of light elements. So far, no convincing evidence for time variation has been found, and the constraints are tight, but the possibility cannot be ruled out entirely. If the constants do vary, the variation could be driven by a scalar field, a field that permeates space and whose value changes over time. Such a field would couple to the constants, changing their effective values as the field evolves. The field could be the same as the dark energy field, or it could be a separate field. If the constants vary slowly, the effects on the expansion history could be subtle, but they could accumulate over billions of years and lead to observable consequences. If the constants vary rapidly, the effects would be more dramatic, and they would likely have been detected already. The lack of strong evidence for time variation of the constants suggests that if they vary at all, the variation is slow, but this does not rule out the possibility that the constants were significantly different in the very early universe, before the time probed by current observations. There is also the question of spatial variation of the constants, as discussed earlier. If the constants vary from place to place, then the properties of atoms, the spectra of stars, the chemistry of planets, all would depend on location. Our region would have one set of constants, and other regions would have other sets. This is a radical departure from the principle of universality, the idea that the laws of physics are the same everywhere, but is not ruled out by current observations, especially if the scale of variation is larger than the observable universe, or if the variation is small and difficult to detect. Some extensions of the Standard Model, such as string theory and theories with extra dimensions, allow for spatial variation of the constants, and in these theories, the variation is determined by the configuration of the extra dimensions, which could differ from place to place. Let us consider what it would take to definitively prove that we are in a special region. We would need to measure the properties of the universe at distances large enough that we are probing beyond our region, and we would need to find that those properties differ systematically from what we measure locally. For example, if we could measure the Hubble constant at distances of several billion light years, using methods that do not rely on the local distance ladder, and if we found that the Hubble constant at those distances is lower than the local value, this would be strong evidence for a local void or other special structure. Similarly, if we could measure the amplitude of fluctuations at large distances and find that it is higher than the local value, this would support the hypothesis that our region has a lower amplitude due to cosmic variance or special initial conditions. The challenge is that measurements at large distances are difficult and model-dependent. The farther we look, the farther back in time we see, and we must account for the evolution of the universe over that time. This requires a model, and if the model is wrong, the inferred properties could be biased. Breaking this circularity requires observations that are as model-independent as possible, such as geometric tests that rely only on the properties of light and space-time, not on assumptions about the contents of the universe. One such test is the measurement of the angular diameter distance, the relationship between the physical size of an object and its angular size on the sky. If space is flat, the angular diameter distance has a specific dependence on redshift, and deviations from this dependence would indicate curvature or other departures from the Standard Model. Another test is the measurement of the luminosity distance, the relationship between the intrinsic brightness of an object and its observed brightness. The combination of angular diameter distance and luminosity distance can be used to test the consistency of the model and to search for anomalies. Another approach is to look for direct evidence of large-scale structure that could explain why our region is special. If we are in a large void, the void should be detectable in maps of the galaxy distribution, and it should have a characteristic signature in the velocity field, with galaxies flowing outward from the center of the void. If we are in a region with higher or lower dark energy density, this should affect the growth rate of structure, and the effect should be detectable in measurements of redshift space distortions or in the clustering of galaxies. If the fine structure constant or other constants vary spatially, this should leave signatures in the spectra of distant quasars or in the properties of the cosmic microwave background. All of these signatures are being searched for, and the sensitivity of the searches is improving, but so far, no definitive detection has been made. Let us think about the philosophical implications of being in a special region. The cosmological principle, the assumption that the universe is homogeneous and isotropic, has been a guiding principle in cosmology for nearly a century. It is based on the Copernican principle, the idea that we do not occupy a privileged position, and it has been remarkably successful in organizing our understanding of the universe. But if observations require that we abandon the cosmological principle, that we accept that our region is not typical, this would represent a profound shift in our worldview. It would not mean a return to geocentrism, to the idea that the Earth or even the Milky Way is at the center of the universe, but it would mean that the local properties of space, the properties that we measure and use to infer the global properties, are not representative. It would mean that the universe is more complex, more varied than we have assumed, and that our understanding of it is necessarily limited by our location. This shift would have practical consequences as well. If we cannot assume that our local measurements are representative, then we cannot extrapolate them to the universe as a whole with confidence. Our estimates of the age of the universe, the total amount of matter and energy, the ultimate fate of the universe, all would be uncertain, conditioned on our location. We would need to develop new methods for inferring global properties from local measurements, methods that account for the possibility of cosmic variance and special locations. We would need to be more cautious in our claims about the nature of the universe, more willing to entertain alternative explanations, and more aware of the limits of our knowledge. But there is also a sense in which being in a special region would be scientifically exciting. It would mean that the universe is richer and more interesting than a simple, homogeneous expanse. It would mean that there's more to discover, more structure, more variation, more opportunities for new physics. It would challenge us to develop new theories, new methods, new ways of thinking about the cosmos. And it would remind us that science is not about arriving at final answers, but about continually refining our understanding, testing our assumptions, and being willing to revise our worldview in light of new evidence. Let us consider the role of simulations in understanding whether we are in a special region. Numerical simulations of the formation and evolution of large-scale structure have become increasingly sophisticated over the past few decades. These simulations start with initial conditions set by inflation, evolve the density field using the equations of general relativity and fluid dynamics, and produce detailed predictions for the distribution of matter, the properties of galaxies and clusters, and the observable signatures of structure. By comparing the simulations to observations, we can test the standard model and search for discrepancies that might indicate new physics or special locations. Simulations have shown that the universe is not perfectly homogeneous on scales smaller than a few 100 million light-years, and that there are significant variations in the density, the expansion rate, and the growth of structure from place to place. But the simulations also show that these variations average out on larger scales, and that the cosmological principle holds on scales larger than a few 100 million light-years. The question is whether the variations in our local region are larger than what the simulations predict, and whether they're large enough to explain the observed tensions. Some simulations have been performed with initial conditions designed to produce local voids or other special structures, and these simulations have been used to estimate the effects on the Hubble constant and other observables. The results suggest that a local void could produce a few percent effect on the Hubble constant, which is in the right direction, but not quite large enough to fully explain the tension. More refined simulations, with higher resolution and more realistic physics, are needed to definitively answer this question. Simulations also allow us to explore the effects of different cosmological models, such as models with dynamical dark energy or modified gravity. By running simulations with these models, and comparing the results to observations, we can test whether the models can explain the data and whether they predict other observable signatures. This is a powerful approach, but it is limited by the computational cost of the simulations and by the uncertainties in the input physics. Simulations require assumptions about the properties of dark matter, the behavior of gas and stars, the feedback from supernovae and black holes, and many other processes, and these assumptions introduce uncertainties into the predictions. Improving the simulations requires better understanding of the underlying physics, and this in turn requires more observations and more theoretical work. Let's now think about the timeline for resolving these questions. The Hubble tension and the S8 tension have been recognized for about a decade, and they have intensified as the measurements have become more precise. The next decade will see a new generation of observatories and experiments that will provide much more data and much higher precision. The James Webb Space Telescope is already operating and will measure Cepheids and more galaxies and extend the distance ladder. The Vera Rubin Observatory will begin operations soon, and it will survey the entire southern sky every few nights, providing a time-domain view of the universe and measuring the positions and shapes of billions of galaxies. The Euclid mission has been launched and is beginning to collect data, and it will map the large-scale structure of the universe with unprecedented precision. The Simons Observatory and other next-generation microwave background experiments will measure the polarization of the microwave background and probe smaller scales, testing for deviations from the standard model. Gravitational wave observatories are being upgraded and expanded, and the detection rate of neutron star mergers is expected to increase significantly in the coming years. Each detection provides an independent measurement of the Hubble constant, and as the number of detections grows, the statistical uncertainties will shrink. The 30-meter telescope and other extremely large telescopes will allow us to study individual stars and stellar populations in distant galaxies, refining the distance measurements and reducing the systematics. New missions are being planned to measure the cosmic microwave background from space, with even higher sensitivity and angular resolution, and to map the distribution of hydrogen gas in the universe, which traces the large-scale structure and provides an independent probe of the expansion history. All of these observations will converge over the next decade or two, and they will either resolve the tensions or confirm them. If the tensions are resolved, we will have a better understanding of the systematics and a renewed confidence in the standard model. If the tensions are confirmed, we will be forced to consider new physics or new explanations, including the possibility that we are in a special region. Either outcome will advance our understanding and open new avenues for research. But there is also the possibility that the answer is more subtle, that the tensions point to a deeper issue with how we define and measure cosmological quantities, that the problem is not with the data or the model, but with the concepts we use to describe the universe. This would require a more fundamental rethinking of cosmology, a move beyond the simple Friedman-Robertson-Walker model to a more sophisticated treatment of inhomogeneity and averaging, or perhaps even a reformulation of general relativity in a way that is better suited to describing a complex, structured universe. This is a longer-term project, one that will require both observational and theoretical advances, and it may take decades to fully resolve. Let us consider the implications for our place in the cosmos. If we are in a special region, it does not change the fact that we are part of the universe, subject to its laws, and connected to its history. It does not make us the center in any meaningful sense, because the specialness would be a statistical accident, a consequence of the random distribution of matter and energy, not a reflection of any fundamental role or purpose. It would simply mean that the patch of space we happen to inhabit has properties that differ from the average, much as a particular region of a forest might have more trees or fewer trees than the average, without any deeper significance. But it would change how we think about the universe as a whole. If our measurements are biased by our location, then the universe beyond our observable horizon might be very different from what we infer from our local observations. The total amount of matter and energy, the ultimate fate of the expansion, the statistical properties of structure, all could be different. We would need to be more humble in our claims, more aware that our knowledge is limited by our perspective, and more open to the possibility that the universe is more complex and more varied than we can directly observe. It would also raise questions about the nature of scientific knowledge itself. Science is based on the idea that we can discover universal laws by making observations and testing hypotheses. But if our observations are not representative, if they are biased by our location or by selection effects, then the laws we discover might not be universal. They might be local regularities, patterns that hold in our region, but not everywhere. This does not mean that science is futile or that truth is relative, but it does mean that we must be careful about the scope of our claims, about the domain over which our laws apply, and about the assumptions that underlie our inferences. It means that science is an ongoing process, not a finished product, and that we must always be ready to revise our understanding in light of new evidence. Let us now revisit the concept of the horizon, the boundary of the observable universe. The observable universe is limited by the age of the universe and the speed of light. Light from regions farther than about 46 billion light years has not had time to reach us, and so those regions are beyond our horizon, forever hidden from our view unless the expansion of the universe slows or reverses. The horizon is not a physical boundary, but an observational one, a limit to what we can see. Beyond the horizon, the universe continues, and it may have very different properties from what we observe within the horizon. If the universe is infinite, or even if it is finite but much larger than the observable universe, then our observable patch is an infinitesimal fraction of the whole, and there is no reason to expect that it is typical. The horizon also plays a role in the definition of cosmological quantities. When we speak of the Hubble constant or the density of matter, we are implicitly averaging over some volume, and that volume is limited by the horizon. Different observers, located in different regions and at different times, would have different horizons and would measure different averages. The Hubble constant measured by an observer in a distant galaxy could be different from the value we measure, not because the laws of physics are different, but because the averaging volume is different. This is another manifestation of the observer dependence of cosmological quantities, and it underscores the difficulty of making statements about the universe as a whole based on local observations. There is also the question of what lies beyond the horizon. If inflation is correct, the region that underwent inflation is much larger than the observable universe, and the properties of this larger region could be very different from what we see. Inflation is thought to have produced a vast, possibly infinite expanse of space, with different regions having different properties due to quantum fluctuations during inflation. Some regions would have higher density, some lower. Some would have larger fluctuations, some smaller. Our observable universe would be just one small patch within this larger expanse, and there would be no reason to expect that our patch is typical. This is related to the multiverse idea, but it does not require invoking separate universes or different laws of physics. It simply recognizes that the universe produced by inflation is much larger than what we can observe, and that different parts of it can have different properties. If we are in an atypical region within a larger inflated volume, then the cosmological principle would still hold on average over the entire volume, but it would not hold within our observable patch. The universe as a whole would be homogeneous and isotropic on sufficiently large scales, but our local region would not be. This would reconcile the cosmological principle with the possibility that we are in a special region, but would also mean that we can never directly test the cosmological principle because we cannot observe the scales on which it holds. Let's think about the nature of space itself. In general relativity, space is not a fixed background, but a dynamical entity, shaped by the presence of matter and energy. The curvature of space is determined by the distribution of mass and energy through the Einstein field equations, and this curvature in turn affects the motion of matter and the propagation of light. In a homogeneous and isotropic universe, the curvature is the same everywhere, and space can be described by a simple metric, the Friedmann-Robertson-Walker metric. But in an inhomogeneous universe, the curvature varies from place to place, and the metric is more complicated. The question of whether we are in a special region is, in part, a question about the local curvature of space, about whether the geometry of our neighborhood differs from the average geometry of the universe. One way to measure the curvature is through observations of the angles and distances of distant objects. In flat space, the angles in a triangle add up to 180 degrees, and the circumference of a circle is 2 pi times its radius. In curved space, these relations are modified, and the modifications depend on the curvature. By measuring the angles and distances of objects in the cosmic microwave background and in large-scale structure, we can infer the curvature of space. So far, measurements indicate that space is flat, or very nearly so, with a curvature that is less than 1%. This is consistent with the prediction of inflation, which produces a flat universe if the inflationary period is long enough. But the measurements have uncertainties, and there is still room for small amounts of curvature, either positive or negative. If space is not perfectly flat, this could affect the interpretation of observations and the inferred cosmological parameters. A positive curvature, corresponding to a closed universe, would make objects appear smaller and more distant than they are in a flat universe. A negative curvature, corresponding to an open universe, would make objects appear larger and closer. The Hubble constant and other parameters would need to be adjusted to account for the curvature, and this could potentially alleviate some of the tensions. However, the curvature inferred from the cosmic microwave background is very close to zero, and it would require a very specific value of the curvature to resolve the tensions, which seems unlikely. Another aspect of the geometry of space is its topology, the global shape and connectivity of space. Even if space is locally flat, it could have a non-trivial topology, such as being a torus or a more complicated manifold, where traveling far enough in one direction brings you back to your starting point. A non-trivial topology would introduce correlations in the cosmic microwave background on large scales, because photons could travel around the universe and create multiple images of the same structures. Searches for such correlations have been performed, and so far, no evidence for a non-trivial topology has been found, but the searches are limited by the size of the observable universe and by the noise in the data. If the universe does have a non-trivial topology, and if the scale of the topology is comparable to or larger than the observable universe, it would have implications for the interpretation of the cosmological principle and for the question of whether we are in a typical region. Let us return to the question of dark matter and its role in determining the properties of our region. Dark matter is thought to make up most of the matter in the universe, but its nature remains unknown. The leading candidates are weakly interacting massive particles, or WIMPs, but despite extensive searches, no WIMPs have been detected directly. Other candidates include axions, which are very light particles that could be produced in large numbers in the early universe, and primordial black holes, which could have formed from density fluctuations in the early universe before the formation of stars. Each of these candidates has different properties and would have different effects on the formation and evolution of structure. If dark matter consists of WIMPs, the particles would be nearly collisionless, interacting only through gravity and possibly through the weak nuclear force. This is the assumption in most simulations of structure formation, and it produces results that are consistent with observations on large scales. But on small scales within galaxies, there are some discrepancies between the predictions and the observations, such as the cuspy halo problem, the missing satellites problem, and the too big to fail problem. These discrepancies have led to proposals for alternative forms of dark matter, such as self-interacting dark matter, where the particles scatter off each other, or warm dark matter, where the particles have higher velocities and suppress the formation of small structures. If the nature of dark matter is different from what we have assumed, this could affect the inferred density and distribution of dark matter in our region, and it could contribute to the tensions. If dark matter consists of axions, the particles would be extremely light and would behave as a coherent wave on small scales, forming structures called axion stars or axion halos. These structures would have very different properties from the dark matter halos predicted by WIMP models, and they could affect the formation and evolution of galaxies. Axions are also a candidate for dark energy in some models, and if this is the case, the distinction between dark matter and dark energy would be blurred, and the properties of both would be intertwined. This could lead to new effects on the expansion and the growth of structure that are not captured by the standard model. If dark matter consists of primordial black holes, the black holes would cluster gravitationally just like any other form of matter, but they would also have additional effects, such as gravitational lensing of background light, and the possibility of mergers that produce gravitational waves. Recent detections of gravitational waves from black hole mergers have raised the question of whether some of these black holes could be primordial, formed in the early universe rather than from the collapse of stars. If a significant fraction of dark matter is in the form of primordial black holes, this would have implications for the interpretation of gravitational lensing observations and for the inferred density of dark matter in our region. Let us think about the role of baryonic matter, the ordinary matter made of protons, neutrons, and electrons. Baryonic matter makes up only about 15% of the total matter in the universe, but it is the matter that we can observe directly through the light it emits or absorbs. The distribution of baryonic matter is closely tied to the distribution of dark matter, because baryons fall into the gravitational potential wells created by dark matter. But baryons also have complex physics involving gas dynamics, star formation, supernova feedback, and the growth of supermassive black holes, and these processes can affect the distribution of dark matter and the overall structure of galaxies and clusters. In our local region, the distribution of baryonic matter could be different from the cosmic average, due to the particular history of star formation, galaxy mergers, and other events. If our region has a higher or lower fraction of baryons in stars versus gas, or a higher or lower rate of star formation, this could affect the observed properties and contribute to the tensions. For example, the brightness of type I supernovae depends on the metallicity of the progenitor stars, and if the metallicity in our region is different from the metallicity in distant regions, this could introduce a systematic bias in the distance measurements. Similarly, the clustering of galaxies depends on the relationship between galaxies and dark matter halos, and if this relationship varies from place to place, it could affect the inferred growth rate of structure. The role of feedback, the energy and momentum injected into the gas by supernovae and by active galactic nuclei powered by supermassive black holes, is particularly important. Feedback can heat and expel gas from galaxies, suppressing star formation and altering the distribution of baryons. The strength and efficiency of feedback depend on the properties of the galaxies, such as their mass and their star formation rate, and these properties could vary from region to region. If feedback is stronger in our region, it could reduce the density of baryons in galaxies and clusters, and it could affect the observed lensing signal and the inferred matter density. Understanding the details of feedback requires high-resolution simulations and detailed observations of individual galaxies, and it is an active area of research. Let us consider now the concept of time in cosmology. In general relativity, time is not absolute, but is part of the fabric of space-time, and it is affected by gravity and motion. In a homogeneous and isotropic universe, there is a natural notion of cosmic time, the time measured by an observer who sees the universe as isotropic. This is the time that appears in the Friedmann equations, and it is the time used to describe the age of the universe and the expansion history. But in an inhomogeneous universe, the notion of cosmic time becomes ambiguous. Different observers, located in different regions with different densities and different expansion rates, would have different notions of time, and there would be no single universal clock. This raises the question of what we mean when we say the universe is 13.8 billion years old. This number is the cosmic time since the Big Bang, measured in the frame in which the cosmic microwave background is at rest. But if we are in a region where the local expansion rate is different from the cosmic average, the local time, the time measured by a clock in our region, could be different from the cosmic time. The difference would be small because the gravitational time dilation effects are weak on cosmological scales, but it is not zero, and in principle, it could be measured. If we could compare the age of the oldest stars in our region to the age of the oldest stars in a distant region, and if we found a systematic difference, this would be evidence that the local time is different from the cosmic time, and that we are in a special region. Time dilation also affects the observed properties of distant objects. Light from a distant galaxy is redshifted not only because of the expansion of space, but also because of the relative motion of the galaxy and because of the gravitational potential along the line of sight. These effects are usually small compared to the cosmological redshift, but they can be significant in some cases. For example, light passing through a cluster of galaxies is gravitationally blue-shifted as it falls into the cluster and red-shifted as it climbs out, and if the cluster is moving, there is an additional Doppler shift. All of these effects must be accounted for when interpreting the redshifts of distant objects and when inferring the expansion rate. Let us think about the ultimate fate of the universe. In the standard cosmological model, the universe will continue to expand forever, driven by the repulsive effect of dark energy. The expansion will accelerate, and galaxies will move farther and farther apart. Eventually, the universe will become cold and empty, with only isolated remnants of stars and black holes scattered across vast distances. This is called the heat death of the universe, and it is the inevitable outcome if dark energy is a cosmological constant. But if we are in a special region, if the properties of dark energy in our region are different from the cosmic average, then the fate of our region could be different from the fate of the universe as a whole. Our region might expand more slowly or more quickly, and its ultimate fate might be different. If dark energy is not a cosmological constant but a dynamical field, its properties could change over time, and the fate of the universe could be different. If the dark energy density decreases over time, the expansion could slow down, and the universe might eventually recollapse in a big crunch. If the dark energy density increases over time, the expansion could accelerate even more, leading to a big rip, where the expansion becomes so fast that galaxies, stars, and eventually atoms are torn apart. The fate of the universe depends on the equation of state of dark energy, the ratio of its pressure to its energy density, and on how this ratio changes over time. Current observations constrain the equation of state to be close to -1, the value for a cosmological constant. But there is still some room for variation, and future observations will narrow the constraints. Let us consider the implications for the search for extraterrestrial life. If we are in a special region where the density of matter or the expansion rate is different from the cosmic average, this could affect the conditions for the formation of planets, the stability of planetary systems, and the emergence of life. For example, if our region has a higher density of heavy elements, produced by earlier generations of stars, this could make the formation of rocky planets more likely. If our region has a lower rate of supernova explosions or gamma-ray bursts, this could make the environment safer for the development of complex life. These factors are speculative, and we do not yet have a complete understanding of what conditions are necessary for life. But it is possible that the properties of our region, if they are indeed special, have played a role in making the Earth a habitable planet. The search for extraterrestrial life is also connected to the question of how common life is in the universe. If life requires very specific conditions, and if those conditions are rare, then we would expect to find ourselves in a region where those conditions are met, even if such regions are not typical. This is another application of the anthropic principle. We observe the conditions we do because we could not exist under other conditions. But this reasoning is controversial because it shifts the explanation from physics to selection effects, and it is difficult to test. We cannot know how common life is until we actually search for it, by looking for signatures of life on exoplanets, by searching for signals from extraterrestrial civilizations, and by exploring the possibilities for life in extreme environments in our own solar system. Let us now reflect on the nature of explanation in cosmology. In most sciences, we explain phenomena by identifying the causes and mechanisms that produce them. In cosmology, explanation often involves identifying the initial conditions and the laws of physics that govern the evolution of the universe. But if the initial conditions are the result of quantum fluctuations, which are inherently random, then there is a limit to how much we can explain. We can explain why the universe has the large-scale structure we observe, given the initial fluctuations, but we cannot explain why the fluctuations had the particular realization they did. This is a fundamental limit of explanation in quantum mechanics, and it applies to cosmology as well. If we are in a special region, the specialness is likely due to a rare fluctuation in the initial conditions, and there is no deeper explanation for why the fluctuation occurred here rather than elsewhere. The best we can do is to calculate the probability of such a fluctuation and to determine whether it is consistent with the observed properties. This probabilistic explanation is less satisfying than a deterministic explanation, but it may be all that is available. It requires us to accept that some aspects of the universe are contingent, the result of chance rather than necessary, the result of physical law. This contingency also raises questions about the predictive power of cosmology. If our observations are subject to cosmic variance, if they reflect the particular realization of the initial fluctuations in our region rather than universal properties, then our ability to predict the properties of other regions or the future evolution of our own region is limited. We can make statistical predictions based on the distribution of fluctuations, but we cannot make deterministic predictions about specific outcomes. This is similar to the situation in quantum mechanics, where we can predict the probabilities of different outcomes, but not which outcome will occur in any particular instance. Let us consider the role of confirmation bias in the interpretation of cosmological observations. Confirmation bias is the tendency to interpret data in a way that confirms our pre-existing beliefs and to discount data that contradicts them. In cosmology, the Standard Model has been so successful for so long that there is a natural tendency to interpret new data within the framework of the Standard Model, to assume that any discrepancies are due to systematic errors or statistical fluctuations rather than to failures of the model. This is not necessarily wrong, because most discrepancies do turn out to be due to errors or fluctuations, but can also delay the recognition of genuine problems and the exploration of alternative explanations. The Hubble tension and the S8 tension have been recognized and debated for years, and there is still no consensus on whether they represent real failures of the Standard Model or whether they will eventually be resolved. The debate reflects the difficulty of distinguishing between statistical fluctuations, systematic errors, and genuine new physics, especially when the discrepancies are at the level of a few standard deviations. It also reflects the difficulty of updating our beliefs in light of new evidence, of balancing the conservatism that comes from the success of the Standard Model with the openness required to recognize when the model is incomplete. Let us think about the social and collaborative nature of cosmology. Cosmology is not done by isolated individuals, but by large collaborations, involving hundreds or thousands of researchers, working with data from major observatories and experiments. The interpretation of the data requires complex statistical analyses, simulations, and models, and different researchers may use different methods and make different assumptions. This diversity is a strength because it allows for multiple independent checks and reduces the risk of unrecognized errors, but it also leads to debates and disagreements about the interpretation of the data. The resolution of these disagreements requires careful comparison of methods, reanalysis of data, and ultimately, the accumulation of more data that can discriminate between the different interpretations. The Hubble tension is a good example of this process. Multiple teams have measured the Hubble constant using different methods, and they have obtained results that are broadly consistent with each other but discrepant with the value from the cosmic microwave background. This has led to extensive discussions and debates, with some researchers arguing that the tension is real and points to new physics, and others arguing that it is due to unrecognized systematics. The debate is ongoing, and it will not be resolved until more data are available and the systematics are better understood. This is the normal process of science, and is how we make progress. Let us return to the central question: what does it mean to be inside a region of space where physics does not add up? It means that the observations we make, the properties we measure, do not fully conform to the expectations derived from the Standard Model of cosmology, under the assumption that our region is typical. It could mean that our region is not typical, that it is a rare fluctuation in the density or the expansion rate or some other property. It could mean that the standard model is incomplete, that there is new physics, new fields, or particles, or interactions that we have not yet discovered. Or it could mean that our understanding of how to connect local observations to global properties is flawed, that the process of averaging and extrapolating is more subtle than we have assumed, and that the simple models we use do not capture the full complexity of the universe. All of these possibilities are being explored, and the answer will emerge from the accumulation of more data, more precise measurements, and more sophisticated analyses. The process will take time. It will require patience and rigor. But the effort is worthwhile because the answer, whatever it is, will deepen our understanding of the universe and our place within it. If we are in a special region, it will teach us about the nature of cosmic variance and the limits of the cosmological principle. If there is new physics, it will open new avenues for exploration and potentially revolutionize our understanding of the fundamental forces and constituents of nature. If the problem is with our methods, it will force us to develop more sophisticated tools for connecting the local to the global, the observed to the inferred. The journey toward understanding whether we are in a special region is emblematic of the scientific enterprise itself. It is a journey that begins with curiosity, with the recognition of patterns and anomalies in the data. It proceeds through careful measurement, rigorous analysis, and critical evaluation of hypotheses. It involves collaboration, debate, and the willingness to revise our beliefs in light of new evidence. And it leads not to final certainty, but to deeper understanding, to a clearer picture of the universe and of the principles that govern it, whether we are in a special region or not. The effort to answer this question is itself a testament to the power of human reason and the enduring quest to understand the cosmos in which we find ourselves.